Okay, Assalamualaikum, and today I would like to have some presentation for introduction to CAD FLOW. Okay, before that, my name is Ahmad Anwar bin Zainuddin. So today we will see the CAD FLOW, and I will introduce you the flow of the CAD design. Okay, and it will followed by the introduction to quarters 2 using the Altera Quarters Prime is a computer-aided design software to make it easy to implement a desired logic, okay, by using a FPGA or field programmable gate array. So the effort of a complex VSI component may be broken into several steps, okay, several distinct level, each level being stepwise refinement of previous level. So as you can see in the slide, device, circuit, and gate level are classified under VSI subject, while under module and system can be associated in the resistor, transistor logic, or RTL. So basically, if you want to know, all right, for the gate, circuit, and device, normally we call as a front end, okay, front end process, which is the designer need to know basic design or layout, okay, from the schematic, and they need to generate to the layout, okay, generate to the layout, and need to follow to the specific process technology. So all the process technology have their own protocol, okay, and they need to have a different or unique size, okay, unique size or unique measurement from each device or from each circuit and gate, okay. And for the RTL is more on the integrated based on the system and module, okay. So we need to integrate from the gate, and then we need to have a module. We need to follow the communication inside this module to have a good conversation to the system, okay, based on the specific application. All right. So CAD tool products, there are a number of CAD design. For the example, we have the well-known vendor which is called as Altera. So this Altera, they have their product called as Quarters 2, which is we will learn on the coding part. Okay, we will use the VHDL or Verilog to set as a synthesis process. Okay, maybe we need to have some of the flow, okay, as what we will learn in this slide later on, okay, before we jump to the coding section. So this is the CAD flow to design the logic circuit. So they are usually packaged together into a CAD system, which will typically include tools for the following tasks: design entry, synthesis, and optimization, simulation, and physical design. So basically, these all are the flow we need to follow for this design flow. Okay, number one, for the design conception is what the circuit is supposed to do and the formulation of each general structure. So before we start to design, we need to have some of the basic concept. We need to have the basic framework, what we want to design. Okay, if you want to design basically a flip-flop, okay, basically the XOR or NOR gate, for example. So we need to have the initial plan, okay, before we start to design. Maybe we need to think of the chip configuration, okay, in this design, okay, in this design, and we must have the expectation, okay, when we want to have a real figure in the floor plan later on, we must set everything, the size, everything must be precise, easy for the guy who conduct the chip configuration on the floor plan. Okay, for example, so they can have some of the backup plan or the next step to prepare, okay, when they have some limitation occur. All right. Next, in the designer must have the design entry using a schematic of VHDL to design the specification of IC design. So the process of generating logic circuit from an initial specification, and they can manipulate the user design to automatically generate an equivalent but better circuit. So as you can see, we can use or construct any logic design such as a NAND or NOR, NAND and NOR on the board diagram. So, so we can have the Verilog and VHDL, which is can be used to help the designer to draw the number of logic from schematic into codes. So using this code, okay, using this code will easier for the designer to do the repetition of many logic circuit, okay, so that we can use this coding. Okay, this code can have some of the generate more logic circuit or amount number of logic circuit. Okay, instead of we need to have some clear visualization on the schematic, means that we no need to draw. Okay, we need to draw, but we use the code, easy for the designer to do the repetition. Okay, because some of the supplier, they need, maybe they need high production. Okay, they need some of the many quantity. Okay, but we need to have some of the code using the VHDL or Verilog. So after that, so we move to the synthesis. Okay, for the synthesis, we have three sections: netlist generation, gate optimization, and technology mapping. So for the netlist generation, we want to show the syntax error. If the netlist have the error, we need to fix. Okay, when this error has been fixed, it will convert into the netlist. So the second optimization is about the gate optimization, so that we will modify the netlist to obtain the equivalent circuit model. So from this equivalent circuit, it will optimize the goal to be achieved, such as to reduce the cost, okay, to reduce the size, okay, to reduce the delay, and maybe we want to increase the speed. So after we have optimized this, we can move to the technology mapping. Means that technology mapping is an essential step in an FPGA design flow. It is the process of converting, okay, we can see here. This is the process to converting a network of technology independent logic gates, okay, into a network, okay, into a network comprising logic cell on the target FPGA device. So this is the process of the technology mapping. Basically, we have the input and the output. So from the input, a set of CAD and a Boolean network. Okay, then we want to integrate to have a netlist. Okay, a netlist of a gates implementing the Boolean network. So for example, okay, this one is the code, VHDL code. Okay, so this VHDL code, okay, after we write the VHDL code or Verilog code, we need to synthesize. Okay, we need to synthesize to become the schematic diagram. So this is the sample, okay, the sample from this code that we have generated. So if we have so many or a large amount of the logic gates, so maybe you can use this code to have a large number of the devices or component. So we can integrate to the schematic diagram simple like this. Okay, so in order to have this final schematic diagram, we must use the Verilog or VHDL code. Okay. Okay, so next is the functional simulation is to verify that the design will function as expected, means that the design should be correct before to the next step. So for the next, after that, we have the physical design. Physical design to determine the placement of specific logic element and the wiring connection that have to be made between these elements to implement the desired circuit. Physical design consists of three components, which are placement, location, routing, and for the location, the logic gate, and finally static timing analysis. Okay, so this is the three components: placement, routine, and static timing analysis. So from the design has the timing delay of 10 nanosecond, next has 15 nanosecond, and we calculate all this when it will return to report static timing analysis. So this is the example of the step ASIC physical design. So in the physical design, we need to have this kind of the procedure need to follow. Okay, step by step. And finally, we generate the timing closure. Okay, or timing static timing analysis. Okay. Okay, so next is the timing simulation is evaluate the expected delays of design logic circuit. So basically, we want to calculate the propagation delay. So basically, the propagation delay is one of the requirement. Okay, because we cannot produce this on the target. That means we have some of the propagation. We must have a target which is we have maybe at least or below than the target. Okay, the target which is we need to follow normally around 30%. Okay, normally around 30%. And next is the finally, after we have met the requirement, the circuit implemented on an actual chip means after you have run all the VHDL into the FPGA and that is to run. So we can have the chip configuration at the final stage. So this is all the CAD design flow. Okay. So I hope you understand before we move to the code. Okay. And thank you.